Hi everyone, I'm Chen-Chia. Today I'm going to present our work from Duke University and NVIDIA Research, DRC Coder, Automated Design Rule Checking Code Generation. This is today's outline. I'll first make an introduction and then detail the methodology of DRC Coder. And then I will talk about our experimental results and show our conclusion. So let's begin with the introduction. Let's begin with the motivation. So design rule checking is an essential step in physical design flow. Every place and route tool will need an integrated DRC checker to provide the design rule violation feedback to the place and route engine to do the optimization. However, the development of such integrated DRC checker presents some challenges. So first, we need to look at the design rule manual provided by Foundry. So in this manual, it is typically comes with an image and a very succinct text. So the human engineer need to observe both the information to know what's going on this design rule. And also we need to analyze the extracted layouts and the design rule violation that gives from the commercial DRC tool reports. So this figure shows the example of the layouts and the design rule violation that provided by commercial tool. So the engineers need to analyze this information to know more details about the design rules. So these two steps we will call it the interpretation. And after the interpretation, we need to do the coding to write out our DRC checker code. And then finally, we need to check the alignment between the DRC checker with the commercial tool reports to see if our checker can meet the industrial standards. But however, this process needs several rounds of debugging to have a good DRC checker. And this process is traditionally all done by human. So need to take about days and weeks to develop such DRC checker. So we are thinking whether we can automate this DRC coding process. So inspired by the recent advance in the large language model and the vision language model's ability in code generation and image interpretation, we are thinking how we can use the LLM and the VLM to help us doing this DRC code. So we are thinking in interpretation, we can use the LLM and the VLM to incorporate together. And in the coding, we can use the LLM to help us. And finally, to check the alignment, we can design an auto evaluation function to help us to do this. So this whole can be called a system, the LLM agent. So in this paper, we are going to introduce our LLM agent system to automate this DRC code generation process. And we call it DRC Coder. DRC Coder is a multi-agent with vision capability. So it has several advantages. First, it can reduce the development time, and it can increase the coding reliability because right now we have this auto evaluation function, and can avoid some human errors in this alignment checking. And also it can enhance the engineering productivity because right now to generate the DRC checker for a rule only needs to take minutes. And finally, it can enable a more efficient design technological optimization because like right now our DRC coder is developed based on the standard cell automation tool. And the slide shows what our generated DRC checker looks like. Because we are targeting on the place and route system, so this engine will be performed on a grid-based system. So our input of the checker will be a grid-based layout that's shown in the left figure, and our output will be the grid-based design rule violation. So like this is an example generated function that can input the layouts and outputs the DRVs that shows. So this is the goal of our DRC coder to generate. And after we introduce the motivation of the development of DRC checker and introduce the generated code, now we are going to introduce our methodology. So this is the overview of our DRC coder. In our DRC coder, we will separate the interpretation and the coding to be solved by two LLMs. First, we have an agent called planner. The planner will, based on the design rules and input prompts, and to do the interpretation. And the planner will have two tools to call, which is called the foundry rule analysis and the layout DRV analysis. So these two tools, the foundry rule analysis will input the question from planner. So the planner in this example figure, it will ask how me to explain the design rule in detail. And inside this tool, it will have a vision language model that will be prompted by the image of the design rules. And this text is also the prompt, and we will provide the question of planner. And then the VLM will based on the image and the question to answer that. We need to identify some spacing in this design rule and what's the DRC condition for these rules. And the other tool is the layout DRV analysis. The input will be also have the question from planner, and the other input is a list of the cell name that the LLM wants to look at. So in our function, we will automatically fetch the layout of these two cells, and then that the VLM to answer the question from the planner. So right now the planner wants to get the reasons of DRVs, and the VLM can help us identify that based on the left cell. This highlights the spacing issue between the two metals which are too close. And for the right cell, it can note that this indicates that the metal is too close to the cell boundary, which caused a violation. So based on these two tools' response, the planner will give out its final interpretation, which is the example in this figure. So it will provide the analysis of the design rule violations. Also, it will provide the plans to write the DRC code, which we need to check for boundary and we need to check for spacing rule based on horizontal. And so after the planner generates the rule condition, and then there is another LLM called programmer. It will based on rule condition to write out the DRC code. And then this DRC code will be automatically called the DRC code evaluation function to check the alignment of our grid-based DRV with the golden DRV that output from the commercial tool. So here is the detail of how DRC code evaluation tool works. So the input of this function will be the generated DRC code. And inside of this function, we will first run the DRC code on all the cell layouts in our dataset. And then we will compare the design rule violation with commercial tools reports to compute the overall performance. So in the output, we will list out the precision, recall, and F1 score. And then we will report the false negative and false positive. So the false negative will be the missed DRV locations. And then we will help to calculate the distance of the design rule violations in this false negative, and we will also tell the false positive if it exists. And finally, the DRC coder, the programmer can base on this DRC code evaluation tool to do the debugging to solve this false negative and positive. So after talking about the methodology let me introduce our experimental results. And here is our setup. In our work, we target on the layout automation tool on vCells to develop its DRC checker. So we use it to do the layout data generation, and we use a very simple maze routing on it to perform around 200 layouts that have a lot of design rule violations. And this is our evaluation metrics. Because the design rule violation detection problem can be viewed as a classification, so we use the precision, recall, and the F1 score as our metrics. So here's some demonstration of our design rules. We have M0, M1, VR0, VR1, and also an interlayer spacing rule that need to consider both N2 and VR1 metals. And here's our main results. We using two LLMs, Llama 3 and the GPT-4o, and our baseline is standard prompting. And this result shows the design rule checker generation based on for each design rules. And this figure shows that using DRC coder, we can improve based on two LLMs. And also for the GPT-4o, our DRC coder can complete all the codes to have the correct DRC checking. And finally, the average runtime is only 200 seconds for each rows. So in this, we perform some evaluation study to evaluate the impact of VLM and the multi-agent capabilities. So we do some changes of our original DRC coder. We right now using the multi-agent setting, but without the vision language model. And we using the single agent. So right now it doesn't have planner and the programmer, it only has programmer itself, but with the help of VLM. And this result shows that without the VLM and without the multi-agent, we cannot achieve the successful code generation. But with both, we can complete the code. So this shows that the VLM and the multi-agent really helps in the DRC code development process. So let's go into the So here is a conclusion. We developed DRC coder, a multi-agent framework with multi-model vision capability to solve the DRC coding problem. And DRC coder can achieve a perfect F1 score across all design roles that considered in a vCell. And DRC coder can accelerate the development of checker from days to minutes compared to manual work. And our framework have some future directions that can be extended to a wide range of DRC-related applications. So first, it can use to be a DRC explanation chatbot, and also it can perform as a DRC solving copilots that cooperated with human. So thank you so much for listening.